So now I can add 0 to equation 6. It does not change anything to that equation, right? It is essentially 0. So I can add this term to equation 6, okay. So let us go to the next page. I would like to copy this before that. Let me just copy equation. So we have equation 6. Now we are going to add the 0 term, which is, I am going to make this, or subtract, add or subtract. So I am going to make minus ui prime do uj prime by do x do xj, okay. So the 0 term, is added. So now I can write the right hand side. This is minus of, if I use chain rule for products here, I can push the fluctuation inside the differential operator, right. So I can write this as simply dou by dou xj of ui prime uj prime average, okay, using chain rule or product rule. Now the statistical analysis chapter is useful, right. You saw something that we discussed. So what is this last term now? So now this equation is, what is the number we achieved? 7, right? Okay. So let us call this equation 7. So in equation 7, this particular term, we have this ui prime uj prime over bar. So this, if I expand for different I and j values, so I would get 9 terms. So this is a tensor, second rank tensor, 9 terms, and it is a symmetric tensor. Whether it is uj prime ui prime over bar or ui prime uj prime over bar is the same. If you expand it, you would get 9 terms. So the off diagonal terms are same. So it is symmetric tensor. Therefore I get 6 unique terms here, which is u1 prime u1 prime, u2 prime u2 prime, the diagonal components, u3 prime u3 prime, and the off diagonal components u1 prime u2 prime, u2 prime u3 prime, u1 prime u3 prime, and this we gave a name, covariances, cross covariances, in the statistical analysis chapter, right. One varies together because it is a square term. The top 3 are square terms. They are always positive in a turbulent flow. If it is 0, there is no turbulence. So the top 3 terms, covariances or the diagonal components, has to be positive, and this can take positive or negative, correlation or anti-correlation. They can vary together, that is your u1 prime u2 prime, two fluctuating velocities can vary together or vary in the opposite direction. If one is increasing, the other one can decrease at a given point, single point statistics, because we are essentially evaluating momentum at every location in your spatial domain x, y, z, right, at a single point, and we are looking into how this fluctuating vectors, velocity vectors, are correlated with each other at the same point, okay. So that is why you are now appreciating the statistical analysis. Move to the equation part, okay. So we already had this discussed. This is the so called covariances and the correlation terms, the 6 of them. So again, this is the only term which knows about turbulence, the last term here, right? It's the only term which knows about turbulence term here. The rest are all mean and statistical, okay? These are all statistical part here. The rest of them are completely statistical. Yeah, so before we go ahead and look at how this can be solved, first let us see whether these equations are closed, okay? So now how many equations we have and how many unknowns? So we have in total 4 equations here. Even if you use the mean pressure, the Poisson equation, or using the continuity like before, we will get, so basically we have u1 bar, sorry, we have u1 bar, u2 bar, u3 bar, 3 mean velocities and mean pressure. You can get a Poisson equation for it, or you can use the continuity equation, okay, p bar, or using the continuity equation, let's see. Depends on the way you want to solve. And the unknowns, again I have u1 bar, u2 bar, u3 bar, p bar, and then these 6 extra terms, which is u2 prime, u2 prime, u3 prime, u3 prime, and then I have u1 prime, u2 prime, the correlation terms or cross covariances, 6 extra unknowns. So I have 4 equations here and I have 10 unknowns. Again, closure problem, but here we call this turbulence closure problem, okay. Therefore, number of equations or less than number of unknowns. This is what is called a turbulence closure problem. Now one can argue, what is the big deal here? We had the same problem while looking into the Navier-Stokes equations, right? It was a momentum equation. The momentum equation became Navier-Stokes only upon adding Newton's law of viscosity. Otherwise, it's a general momentum equation. When it was dou tau ij by dou xj, it's a general momentum equation applicable for any type of flow. We consider a Newtonian fluid and we use that model, Newton's law of viscosity, and the equations got closed. So one can also argue here, why don't we do the same thing here? We can just assume turbulence is a viscosity term, but turbulence is not viscosity. That is the problem, right? So there you had a help, you had this molecular viscosity or a property of the fluid was helpful. You can consider air, water, or some particular Newtonian fluid, you know the viscosity value, and therefore you could close it. The mu was known, right? You essentially related that 6 unknowns tau ij to a molecular viscosity mu and the velocity gradient, which is UVW, which is known anyway. So the only new information required was molecular viscosity, which is known to you. So therefore the equations got closed. But here if you use the same concept, there is nothing called turbulence viscosity, because turbulence has nothing to do with viscosity, okay. Turbulence we already characterized, it does dissipation, it does diffusion, that is transport, okay. Viscosity also does transport. viscosity can also do dissipation, but turbulence does more than that. It has many other characteristics. So it doesn't act only like it is dissipative or just diffusive, and therefore it cannot be considered as a viscosity term. So it is not straightforward here. The model is not straightforward and not as good as the model that we achieved in the Navier-Stokes equations. That is a better equation, closed form, completely coming from first principles. Here equation is fine, but it remains unclosed. Okay. So the idea here, note the idea of closing these 6 unknowns using a, I'll use quote like a turbulence viscosity. Okay, the idea of closing these 6 unknowns using a turbulence like viscosity does not help, because turbulent flows are just turbulent flows. It's a flow, unlike the viscosity, which was a property of the fluid. Here, whatever you want to call it, even if you want to call it a turbulence viscosity, it is a property of the flow, not the fluid. Okay, so then it will be a problem. Does not help, since the so called turbulence viscosity will be a property of the flow, not the fluid. It is unlike your Newton's law of viscosity. So that kind of an idea we can use it definitely, but it is not as straightforward as before, and one must be ready to accept some error coming out of this assumption. So we will come to that class of models, the so called RANS models, then we will see what it does there. Okay. One more important part I want you to grasp is that what do we call this term? This term has a special name. Okay. So this so called ui prime uj prime, and take another note here. So this ui prime uj prime, this has a name called Reynolds stresses, since we did Reynolds decomposition and averaging. So this is called Reynolds stresses. So why did we or anybody called it Reynolds stresses? The question is it a stress here? If you go back, is it really a stress or is it something else? See, this term has its origin from the non-linear term. It is just a correlation. Its physical meaning is it's a correlation. It's a non-linear correlation term, and it's the origin of turbulence. It knows about turbulence. It's non-linear and it's a correlation. It is not a stress. So then why is it called stress? Not to solve. Its dimensions are like stress. So if you take here this particular equation, let's rewrite that only the stress term here. So before that, write it down here. Reynolds stress it is not a stress term, but a non-linear interaction term, or simply you can say a correlation term. So why did we call it a stress is because if you rewrite the viscous term and the Reynolds stress term, that is these two terms, the new dou square ui bar by dou xj square and this term. If I rewrite this, you would get, so rewriting last two terms in equation 7, right? Equation number 7, yes. I can write this as dou by dou xj of mu by rho dou ui bar by dou xj, right, this particular term, and this one. Both are minus, yes, plus I have, sorry, dou by dou xj of ui prime uj prime over bar. The mu by rho, yes. So now if I multiply throughout by density, I can rewrite this simply as if I take this down, then I would get this last term as, so this will be simply mu dou ui bar by dou xj, right? So this will be mu dou ui bar by dou xj. This is your viscous stress. Then this term will be rho dou by dou xj of, wait, did I make a mistake? Yes, there is a mistake. So this differential operator does not exist, right? I am taking it out here. So dou by dou xj is the one differential operator, I am taking it out. So viscous term, it survives because it's a second order differential term, but here this coming out, only Reynolds stress remains, correct? So only this term is surviving here. So only, so it is ui prime uj prime over bar, okay. So if I multiply throughout by density, I would get this, and here I would get rho ui prime uj prime, okay. And this is your viscous stress tensor, and since you are able to write two terms together, one is a stress, the other one has the units of stress. So if you look into this, this is Newton per meter square now. This is your viscous stress. Since this term has units of stress, therefore this term has units of stress and can be written together with the viscous stress term. Thereby the name came. Thereby it's called Reynolds stresses. But you must remember that it is not a stress, not a stress term. Its true meaning is basically it has nonlinear interaction term that represents, and you can think it of as a correlation term, a nonlinear correlation term, not really a stress, but popularly called Reynolds stresses. So if we can close Reynolds stresses, the equation 7 for mean momentum gets closed, and then you can solve for mean velocities, solve for mean pressure, and get whatever engineering data you want to achieve. Okay. So the takeaway here is that by Reynolds decomposing and averaging, you basically introduce new unknowns into the equation, and therefore there is a turbulence closure problem. The equations are not possible to solve in a simultaneous fashion because you have 4 equations, 10 unknowns, you cannot solve this, and this extra 6 terms has the name Reynolds stresses, but not really a stress, but takes the unit of that stress.